Chapter 2, Chemistry. So we're going to look at some fundamentals of chemistry. It's not intended to replace a chemistry course, but to give you enough chemistry understanding to follow the physiology of what we're going to do for the rest of the semester or two. So we start at the beginning. There are the concepts of matter and energy. Matter is anything that has the property of mass and occupies space. Mass is the property that it interacts with gravity, that gravitational force works on it. Matter comes in, we're going to say 3 states, because that's what this says. It can be argued that there are 4. Solids, liquids, gases, and potentially plasma. So solids have a definitive shape and volume. They don't change volume. Liquids have a definite volume, but the shape will change to suit the container. And gases change in shape and volume. And really the difference between these 3 is the amount of energy. Solids have less energy, liquids have more, and gases have even more energy in them. And energy can be really defined as heat. Now, energy is the capacity to work, or which is move a mass through a distance, motion. It doesn't necessarily mean that the matter is moving, because if the energy is there to do it, but the movement's not happening, we call that potential energy. Kinetic energy is energy that is in action, that is actually doing the moving. Imparting potential energy into matter can be just simply lifting something up, so that amount of matter has further to move. But nevertheless, stored energy is potential. Kinetic energy is energy that's actually doing work. Now, potential energy can be stored as chemical energy, and that's really stored in the bonds of molecules. That when atoms are joined together in the forms of bonds, that represents a stored energy, a potential energy. It can be released as kinetic energy when the bonds break. So forming bonds will store energy, breaking bonds release energy. I'll say it again because it's fundamentally important. Creating bonds, making bonds between molecules or between atoms in a molecule, is a way of storing potential energy. Breaking those bonds is a way of releasing that chemical energy, or that potential energy. Now, electrical energy is the result of movement of charged particles. So that could be electrons, could be protons, could be ions, positive and negative ions. Anything that is electrically charged and moves gives off an electrical energy. This is, by definition then, a kinetic energy. Mechanical energy is directly involved in moving matter. So that would be things like the explosion in the cylinder of your car, where the potential energy of the chemicals, the bonds found in the gasoline in the car, is released as kinetic energy and becoming the mechanical energy of moving the cylinder. We put octane, which has 8 carbon-carbon bonds into the cylinder, and with the spark, we have a chemical reaction that turns it into 8 carbon dioxides and water, and the energy released by that chemical reaction becomes the kinetic energy, the mechanical energy of moving the pistons. Radiant energy is electromagnetic. So it's wave-like properties. So this is light, X-rays, gamma rays, things like that. So it's the whole spectrum of electromagnetic energy. And it radiates from a source. That's why it's called radiant energy. Now, as I've already kind of alluded to back in this slide, these forms of energy can be converted from one to another. That potential energy stored as chemical energy can become kinetic energy, mechanical energy. Some of that energy is lost to heat, which is radiant energy. And some of it becomes electromagnetic through the piezoelectric effect. But the point here is that energy can go from one form to another, and that energy is conserved. The amount of energy on one side of the reaction is equal to the amount of energy on the other side of the reaction. Energy is not lost, it's just that conversions aren't complete, and anything that's incomplete radiates as radiant energy, heat. So the conversion from chemical energy to mechanical energy is by no means complete. The heat of your engine proves that. The fact that we need a radiator, the fact that if you run the engine for a while, you can't touch it, because the radiant energy of heat is that mark of inefficiency. It doesn't become totally mechanical energy. Okay, so now we'll talk about some of the components of matter. So matter is primarily consists of things called elements. These are atoms, and they are kind of the fundamental building blocks of matter. These can't be broken down by ordinary chemical means. They can be smashed in particle accelerators and things. Each element has its own unique properties. These properties are detectable, and they have their own unique chemical properties. They will interact with atoms of different elements in a very specific way. Or they won't interact at all. In the case of the noble gases, the inert gases, there is no interaction. So helium doesn't form bonds with anything. It doesn't interact at all. And that's a unique chemical property in and of itself. So each element is represented by the atom of that element. And you've probably seen this on the periodic table. And on the periodic table, each element has a 1 or 2 letter symbol, the atomic symbol, that represents it, kind of as a shorthand for each element. So when we look at it, oxygen is O, carbon is C, hydrogen is H, nitrogen is N. Those are the symbols. Those 4 things together make up about 96% of our mass, our body mass. Water is hydrogen and oxygen, 2 hydrogens and 1 oxygen, H2O. Proteins are carbons, oxygen, hydrogen, and nitrogen, because there's nitrogen in every amino acid, etc. We'll talk more about that later. But the point is, there are a few other things. You know, about 4% of body mass is made up of things like sodium and aluminum and magnesium and various other elements. But for the most part, when we're talking the chemistry of physiology, we're talking about the chemistry of these particular 4 elements. And so understanding the bonds that these make and how they interact is the important part of biochemistry, of the chemistry of that supports physiology. So this is the other: calcium, phosphorus, potassium, sodium, chlorine, etc. Very little bit are these trace elements: zinc and manganese and chromium, etc. Hardly anything at all. Still essential. That's why they're called these essential trace elements. But they don't amount to any volume. Okay, so when we look at an atom of an element, each element's atoms are unique to that element, but they are made up of building blocks of the same, at this level of chemistry, the same 3 things: protons, neutrons, and electrons. Now the nucleus is the center and the center of mass. Most of the mass of an atom is in the nucleus. And that consists of the neutrons and the protons. The neutrons have no electric charge. Protons are positively charged. Both of these things have a mass of 1 atomic unit. And really, it's useful because protons and neutrons are particles that are the same size. They have the same mass. And since it's the fundamental particle, these are the fundamental particles in the nucleus, we just arbitrarily say that it's 1 atomic unit. The definition of an AMU is the mass of a neutron or a proton. So if the atom has 6 protons in its nucleus and 7 or 8 neutrons, so 8 neutrons, it weighs 14 AMUs. And that happens to be carbon, carbon 14. Electrons flit around the nucleus. These are very, very light particles. We say they weigh 0 AMUs, but really it's 1/2000th of an AMU. It's negligible. There's nothing has 2,000 electrons, so therefore it doesn't contribute to the mass or to the weight of an atom at all. Electrons are negatively charged, and because they're negative, they're attracted to the positive charges of the protons. And because of that attraction, they equal in number to the protons in the atom. So if there are 6 protons in a carbon atom nucleus, that's enough positiveness to attract 6 electrons. And for the most part, we expect the charges to balance each other out. If the if there was only 5 electrons and 6 protons, then the atom would be positively charged and be interacting, trying to grab another electron to balance out its charge. If there was 7 electrons, it wouldn't be strong enough to hang on to that, and it would probably lose the electron. Now here it says that electrons orbit the nucleus. I will take exception to that. In a simplistic look at this, we can say that electrons orbit, but that gives it the idea that it's like a planet orbiting a star, like the planet's orbiting the sun. It doesn't do that. It's more like moths being attracted to a light bulb. Moths are attracted to the light because moths move towards light. Moths are repelled by the heat. And so what happens is the moth gets close and then backs away because the attraction is overbalanced by the heat. It gets far enough away that it's a little bit cooler, and now the repulsion of the heat gives way to the attraction of the light. And so the moth flits around the light bulb at a certain distance so that it doesn't follow any pattern. It just is flitting about. And the electrons do the same thing. Electrons are attracted by the positiveness of the protons, and they're repulsed by some of the other subatomic forces that we won't get into because it becomes too much physics. But suffice it that there's a repulsive force that pushes the electrons away. And so there's constantly this balance where electrons are moving closer because of the attraction, and they're moving further away because of the repulsion. And we're going to find them in the area where those two forces balance, where the repulsive force and the attractive force are more or less balanced. We are not likely to find them close to the nucleus because the repulsive forces outweigh the attractive forces, and they're pushed away. We also are not going to find them too far away because the attraction will outweigh the repulsion and won't let the electrons get too far away. And so the electrons will occupy kind of a sphere around the electron, or around the neutron, the nucleus, I apologize, around the nucleus at a certain distance, more or less. And so the probability of finding the electron close is very low, then the probability is high, and then the probability is low again. And so we can say that the electrons occupy this sphere of high probability. We don't know where in that sphere a particular electron is, but chances are good that it's going to be in that area. So we call this sphere of probability a shell, an electron shell. So the probable regions is like an electron cloud of probable densities. And we use this to predict what's going to happen in forming and breaking bonds with the atom. By understanding this, it helps us understand. We don't use the planetary model at all. So when we look at it, this is the planetary model where the electrons, and you'll notice here there happens to be 2 protons and 2 neutrons, so this is helium. In the planetary model, we have the 2 electrons in a nice defined orbit around the nucleus. That's not what it is. What it is more like this cloud that we might find an electron here, we might find it here, we might find it here, we might find it here. We probably won't find it here, and we probably don't find it really close. This is a probability. Chances are good that the electron will be found within this sphere. And so we call it an orbital or a shell. So each element in the periodic table is defined by the number of subatomic particles. And that's really the number of electrons, which equals the number of protons, and the number of neutrons. And that defines the mass of that atom and the chemical properties of that atom, and therefore it is the properties of the element. So if we look at this, hydrogen, which is 1, has no neutrons and 1 proton, and therefore can attract 1 electron, and that's in the first shell. This is shown as a planetary model. I don't know why they continue to use it. It doesn't matter. Picture this circle as defining the outside of the orbital. And this 1 electron can be found anywhere in this area. Helium is 2, 2, and 2. 2 protons, 2 neutrons, 2 electrons. This electron could be found anywhere in here, this electron anywhere in here. Chances are really good, because the electrons are both negatively charged, they will repel each other and therefore be found kind of opposite, so that if this one moves to here, this one will probably be pushed over to there. So they just flit around like 2 moths around a flame. Lithium is number 3 on the periodic table, and it has 3 protons, 3 electrons, and it happens to have 4 neutrons. So it is number 3 on the table. It weighs approximately 7 AMUs, because the 4 and 3 make 7. Now there are some types of lithium that might have they might only be 3 and 3, so it would weigh 6. But it's very rare. Most of it is this configuration. And you will see that what happens here is that this sphere of probability, this orbital, is just big enough to hold 2 electrons. Once it gets its full 2 electrons, then the 3rd electron is attracted to the proton, repulsed by the forces of the nucleus, but it's also repulsed by the negative charges of the electrons. And so therefore it occupies a sphere around the first sphere. So what we have is low probability of finding an electron, high probability of finding electron, low probability of finding electron, and high probability of finding electron, and then low probability of finding electron. So the shells sit together like nesting dolls, like Russian dolls that nest. The inner shell can only hold 2 electrons. The second shell is much larger, and it actually has room for 8 electrons. We'll see in a minute. Because they can spread out further from each other. We call the shell on the outside the valence shell. This is the valence shell of hydrogen, it's shell 1. Of helium, it's shell 1. Now shell 1 is full, so now this is shell 2 with 1 electron in it. The valence shell has 1 electron. One of the things that's interesting is that the valence shell of this element, hydrogen, has one electron, and the valence shell of lithium has one electron. So the chemical properties of these two elements will be similar because it's the valence electrons that interact with other atoms. And both of these have a valence shell of 1. The atomic number is the number of protons when we look at the periodic table. I'm not going to worry so much about the mass number, but the mass is the mass of the protons and the mass of the neutrons. Anytime that these masses vary, because the number of neutrons vary, we call this an isotope. And we'll just leave it at that. The atomic weight that's listed in the periodic table is the average of the mass of all the isotopes. So if you have 100 that weigh 14 and one that weighs 15, it would be 14.01 would be the weight. It's just the average. So hydrogen, most of them have 1 proton, no neutrons. Atomic weight of 1, or atomic mass of 1. Deuterium, which is a specialized form of hydrogen, has a neutron, so it weighs 2. Tritium has 2 neutrons, so it weighs 3. These two are fairly rare. Sometimes what happens is you have an isotope and it's going to revert from this to this. When it does so, this particle, this neutron that's extra, can't live on its own, so it converts to pure energy. And that energy is radioactivity. And you can detect that energy. And that's what a radioisotope is. It's spontaneously giving energy as it reverts to its more base isotope. We use them for various things. This is how radiocarbon dating works, etc. So most elemental atoms don't exist on their own, with the exception of the noble gases, which helium is one. Most of them form bonds. A molecule is 2 or more atoms bonded together. So H2, 2 hydrogens bond together, is a molecule. Now the molecules can be a molecule of the element, like H2, or they can be a molecule containing different elements. C6H12O6 is a carbohydrate. It happens to be glucose. There are 6 carbons attached to 12 different hydrogens and 6 different oxygens, all forming one molecule. Right. Now, we call this, both of these are molecules. We call the hydrogen that only has the one element in it a molecule of that element. We call the ones that have different kinds of elements bonded together compounds. Both of them are molecules, a molecule of element, a molecule of compound. The vast majority of what we deal with are compounds. Now, sometimes stuff gets put together and chemical reactions don't happen. And these things are called mixtures. This is when the stuff is in physical contact with each other. The different molecules are in contact with one another, but they can be separated by mechanical means because they don't form chemical bonds with one another. So there's 3 types of mixtures. One is called a solution, one's called a colloid, and one's called a suspension. So solutions are first. Solutions are what are called homogeneous mixtures. So a solution is when the molecules of a compound are equally distributed in a solvent. The solvent is oftentimes a liquid, but it might be a solid or it might be a gas. It doesn't really matter. What matters is that the molecules are all kind of equal distance apart from one another. And so one part of this mixture is the same as another part of the mixture. So if you take a teaspoon of sugar and you put it in coffee, the sugar will dissolve in the hot liquid, in the solvent of the coffee. And the first sip of coffee will be exactly the same sweetness as the last sip of coffee, because the sugar, by dissolving and forming a solution, gets evenly distributed throughout the solvent. The solvent is generally the thing that's in the greatest amount. Solutes are the things that we put in them, usually in the smaller amount. You can usually see through it because the particles are so evenly distributed that there's no variance and therefore nothing to reflect light. So they're usually transparent. Solutions are usually transparent, not always. But they can be returned and they can be separated back to the constituent parts. If you take sugar and water and you dissolve the sugar in the water and then you evaporate the water out, you're left with sugar. If you have salt in seawater and you take the water away by evaporation, you end up back with the salt. We talk about concentrations of solutions as the parts of this solute in the solvent. And we can get into Avogadro's number and moles and molarity and things like that. I'm not worried about any of this. Alcohol, for instance, in water is a solution. So the vodka that you drink, if it's 40 proof, is 80% alcohol and 20% water. It's just a way of expressing how concentrated it is. I'm sorry, I said that backwards. It's 80 proof, which is 40%. So proof is double. So it would be 60% water, 40% alcohol in most vodkas, for instance. Colloids are something else entirely. They are called emulsions. They are heterogeneous in that some areas contain more of the solvent and some areas contain more of the solute. They tend to be translucent. You can kind of see through them, but they tend to have color. Large particles don't settle out. Once you put together a colloid, it stays a colloid. So this would be things like Kool-Aid or Jello. That the particles are large enough to be distinguishable from the solvent that you put it in, but they stay suspended. They stay as part of the emulsion. Most colloids will gel, and that's why Jello works. This is all of the creams and gel-like substances that we use, all are colloidal. A lot of proteins do this. Now, almost invariably, the solute in a colloid is a very large molecule, so that's why proteins tend to be found in colloids. The next one is a suspension. Suspension are also heterogeneous, and the solutes are even bigger, to the point where gravity affects them, and if you leave them sit, the solutes will fall out of solution. They will settle to the bottom. So like a mud puddle would be a suspension. Stir it up and it's all muddy. Let it sit there and the soil sinks to the bottom and the water on the top is fairly clear. And so these are suspensions. Now in the body, so here it's saying that blood is a suspension. Well, blood is a suspension as far as the red blood cells, the white blood cells, and the platelets are concerned. If you leave blood sit, the red blood cells will fall out of solution, then the white blood cells, then the platelets, and then above that would be the blood plasma. But the blood plasma has all of these proteins in it, things like albumin and fibrinogen and things like that, antibodies, which are globulins, and those proteins are colloids. That's why blood will form a gel. It will clot to a gel. But blood also has things dissolved in it, things like oxygen, sodium, chlorine. Those things are actually solution. So a lot of these things are at the same time solutions, colloids, and suspensions. All of your interstitial fluid, all of your lymph, all of the fluid that's found in your body tends to be all three of these mixtures with oxygen and carbon dioxide and electrolytes dissolved in solution, proteins in colloidal suspension, and cells as suspensions. So this is just a picture of that. Like I say, mixtures, there's no chemical bonding, and they can be separated physically. Compounds, on the other hand, are homogeneous, and there is bonds formed. So there's a chemical interaction between the atoms that make up the compound. And the only way that they can be separated is by breaking the bonds. The compounds, excuse me, don't have the same chemical properties as their constituents. So hydrogen and oxygen have their unique chemical properties, neither of which are the properties of water, which is a compound of hydrogen and oxygen. So they develop their own chemical properties. They develop their own interactions with other compounds, with other molecules. So to go back to what these bonds are, when we looked at these orbital shells, these electron shells, the electrons fill them up, and there's different energy levels around them. I'm not going to worry too much about the energy levels, but we use something called the octet rule. The first shell, the inner shell, has room for 2 electrons, and every other shell, for our purposes, will hold 8. Now this rule is a simplified version of reality, but in terms of physiology, because we are using a limited number of elements, this holds true. So we get 2, 8, 8, 8 in the shells. And they nest with each other. The outer shell is called the valence shell. Now, if the valence shell is shell number 1, and there are 2 electrons, that atom is stable and unreactive. The outermost shell is fully occupied. If it's shell 2 or 3 or 4, that outermost shell has 8 in it. It is inert. It doesn't react, and therefore no bonds will be formed because the outer shell is full. It has 8. So this would be things like neon and argon and those gases over on the right-hand side of the table. All other elements have got a valence shell with that isn't full. So hydrogen is reactive because its valence shell only has 1, and it's the first shell. The next, the 7 that end up in shell number 2, starting at lithium, are all reactive because they do not have a full valence shell. So if we look at this picture, we'll see that helium has 2 shells, or has 1 shell, and it's full, doesn't react. Neon has 2 shells. It's atomic number 10, and doesn't react because it is chemically inert. So how can these shells that don't have the full number, that aren't fully occupied, reach some sort of stability? Well, they either gain, lose, or share electrons. And we do that by forming bonds. And they achieve their stability that way. So if we look at something like hydrogen, how can hydrogen reach a stability here? It either has to attract another electron into its shell, or it has to get rid of this electron and just be a proton. So if it gets rid of that electron, it becomes a cation, a positively charged ion, that has 1 proton and no electrons. It will ionize, right? Sodium here also has 1 in its valence shell. So how can it reach stability? Well, if it ditches this electron right there, now it will have 10 electrons to deal with, 2 and 8, and the valence shell will be full and it will be stable. So sodium will try and get rid of an electron. If we look at chlorine, chlorine has 7 in its outer shell. So how can it reach stability? By gaining an electron. And that's why we find sodium and chlorine together a lot, because sodium's trying to get rid of an electron, chlorine is trying to gain an electron, so they're attracted to each other. Things like oxygen and carbon, however, like for this to reach 8 is almost impossible, because if we were to give away one, then there's more attraction and it holds on to these other ones the most. So it's not strong enough to attract 4 electrons, and it's not able to ditch 4 electrons. So the only thing that carbon can do is share electrons with another atom to reach stability in its valence shell. So we look at the different types of bonds. One is ionic, and ionic is when we either get rid of an electron from the valence shell or we gain electrons to the valence shell, and we will then either have not enough electrons to counterbalance the protons, and we have a positive ion, or we have too many electrons, one too many, and then we have a negative ion. Or we share the valence shells, so that's called covalent bonds, and we'll talk about hydrogen bonds in a couple of minutes. So the ions are, cations are positively charged, they've lost an electron or two. Anions are negatively charged, they've gained an electron. You'll notice that the T in cat looks like a positive sign. So I always remember that positive charged ions are cations because this T looks like a plus sign. Now, when you put a cation, like to form a cation, you have to form an anion because the cation has to get rid of its electron to something, and the anion has to get the electron from something. And so in order to make a cation, you also have to simultaneously make an anion. And then these two things are, these two atoms are attracted to each other because they have the opposite charge through electromagnetic attraction, through magnetism, really. And so that bond is formed because of the attraction of the different charges. So here's the sodium ion getting rid of its valence shell electron in the third shell to end up with 8 in its valence shell. The chlorine ion needs, has 17, so it's got 2, 8, that's 10, and 7. To be stable, it needs 8 out here. So the chlorine ion has 18 electrons and 17 protons. So it's negatively charged. There's more negatives. The sodium ion is positively charged because it's got 11 protons and only 10 electrons. And then sodium and chlorine bond together because of this attraction after exchanging an electron and becomes sodium chloride. That's an ionic bond. They tend to form these large crystals that look like this. And then the crystals can dissolve in water and they come apart. Covalent bonds is when you share. So, so this would be things like this carbon needs 4. These hydrogens each need 1. So if we stick the hydrogens all around the carbon and they share, now sometimes this hydrogen will have 2 and sometimes it'll have none, each one of those, and sometimes the carbon therefore has 8 and the therefore has stability. So we just represent this as a little line, and that's a single covalent bond because it's being shared. So really the valence shell of this electron will go like this all the way around all of these, and the electrons, all 8 of these electrons, will flit about all 5 nuclei. It's like having 5 candles together and the moths circle them all. So the 2 reacting atoms become the resulting. Now, you'll notice that oxygen has 1, 2, 3, 4, 5, 6, 7, 8. So it needs 2 more So there's 8 protons, 8 electrons, 8 protons, 8 electrons. We put them together, and there's 16 protons. There's 16 electrons, but by sharing the outer ones twice, it can reach that octet. It can reach that 8. And so we show this as a double bond, 2 lines. Means 2 electrons effectively are being shared. Nitrogen does the exact same thing, except that it becomes a triple bond because it shares 3. And it's indicated by 3 lines. So the covalent bonds can be equal because carbon with 6 protons and oxygen with 8 will have about the same amount, pretty close to the same amount of attraction to the electrons, so they share them fairly equally. So we can end up with something like CO2. So C needs 4, O needs 2, and the other O needs 2, so they're going to share 2 with each of them. So that can be represented as C double bond O and a C double bond O there. And it tends to be fairly symmetrical. This is called nonpolar because everything is distributed fairly equally. Sometimes they're unequal. So hydrogen only has 1 proton, and the oxygen has 8, and therefore the 6 in the valence shell here and only the 1 in the valence shell in each of these is not shared equally. The electrons will spend more time around the oxygen because they're more attracted, and less time around the hydrogen nucleus because it's less attracted. So it's unequal sharing. And when that happens, we have something that's called polar. And the one end, it tends to be a little bit more positive, and the other end tends to be a little bit more negative because the attraction holds the electrons at this end more often than this. The molecule becomes V-shape and has a polarity, a positive side and a negative side. And that's why water is such a good solvent, is because of this. So when we have these unequal things, we tend to have hydrogen involved with it because hydrogen is very weak. It only has 1 proton. So the hydrogen bonds, then, is an attractive force between these polar molecules, between the positive side of this kind of attracts the negative side of this one, and the negative side of this one, and the negative side of this one attracts the positive sides of these ones. And so there ends up being this structure because of it. And this is called hydrogen bonding. It's what gives water its surface tension. It's what holds water together. When you take even more energy out of that, the water becomes ice because there's not enough energy to keep these things from moving apart. Now, we look at these things as representing energy. The energy represented by this kind of a bond is very weak. The energy represented by an ionic bond is much stronger, and by a covalent bond is even more strong. And the more equal the covalent bond, the stronger the bond is. And that really represents energy. So the analogy that I use is if you think of a covalent bond as a marriage where everything is shared and 2 entities become one through a commitment and sharing. And there's lots of energy invested in that, and if it breaks, lots of energy is released. it's a traumatic thing. Ionic bonds are like dating, where there's an attraction, there are gifts given to back and forth, energy is put into the relationship between the two, but if the bond is broken, there is less energy invested in it and therefore less energy released. And hydrogen bond is like the cute person down at the end of the bar that you're standing near hoping to talk to. There's an attraction there, but there is really nothing invested. It just kind of keeps you hanging around. So not very much energy goes into making this bond, not very much energy comes out of breaking the bond. So chemical reactions are when bonds are formed or when they're broken. When we write them out as an equation, we write the molecular formula for each reactant and then for the products. And they have to balance left to right. So if we look at something like hydrogen plus hydrogen becomes H2, hydrogen gas, that's a reaction. 4 hydrogens and 1 carbon becomes CH4, methane, that's farts. That's a chemical reaction. And the arrow says it goes this way. Now the arrow can go the other way too. We can break this into that, but it's much more difficult. There's 3 fundamental types of reactions. There's synthesis reactions, decomposition reactions, and exchange reactions. Synthesis reactions is when you put things together, so you're combining things. Decomposition is when you are breaking things apart, and exchange reactions are just when you're exchanging components. So in a synthesis reaction, A plus B becomes AB. It involves bonds being formed. We call these type of reactions anabolic. And anabolic, to create an anabolic reaction, takes energy that's stored in the bond. It's like building a wall. You join one brick to another brick. The energy that you put into that wall stays in that wall until you break it. So anabolic reactions store energy. So you get a bunch of amino acids, you join them together as a protein. This is anabolic. It represents storing energy, making something more complex out of its simpler things. Decomposition reactions are catabolic. AB going to A and B. It's the reverse of the synthesis. You break bonds. You release energy when this happens. So you spend a lot of energy building a wall. You tip the wall over and all those bricks come apart. The bonds break. A lot of energy is released. It's noise and dust and, bricks break because of it. Anybody that's under there could get badly hurt. Catabolic is all about releasing energy and breaking things down to its simpler components. The mnemonic or the memory aid that I use is catabolic is what my cat did to my couch. Took a complex thing and reduced it to its simpler forms by scratching the fabric into its threads. So glycogen becomes glucose catabolically. Energy is released. Exchange reactions are energy neutral. AB plus C becomes AC plus B. Bonds are made and broken at about the same rate, and therefore these are energy neutral. It's just converting one to another. So this would be things like adding glucose and ATP, ADP. So the phosphate comes off and blah, blah, blah. It's just exchange. But in this exchange, this plus this becomes this, or this becomes that. the energy that's represented by this phosphate to the other thing bond is transferred. In this way, although the whole equation is energy neutral, this plus this going to this means that this is now at a higher energy and the glucose is at a lower energy. So we can take energy from the glucose and transfer it to the ADP to make ATP, higher energy, because more bonds. We call the redox reactions are reactions in which things are broken down for the energy. Electrons move, electron donors are oxidized, electron acceptors are reduced. So if there's release of energy, the catabolic reactions that I've just been talking about, we call it exergonic because energy is released, exer. Endergonic stores energy, and they tend to be anabolic. If you take the carbon-carbon bonds in propane, there's 3 carbons. You put a spark to it, you end up with 3 molecules of carbon dioxide. This is all catabolic because the 3 carbons of the propane become 3 separate carbon dioxide molecules. The energy that's released is what cooks your food on the barbecue. Theoretically, everything is reversible. A catabolic reaction under certain circumstances becomes anabolic, back and forth, and a lot of it depends on how much energy is there. And it happens depending on the energy requirements. When we have excess energy, we tend to store it in chemical bonds. When we are needing energy, we tend to break those bonds and release the energy. The rate of the reaction depends on what the temperature, so the heat around. So more temperature, higher rate of reactions. Smaller particle size is a higher rate because there's less to move. The amount of each of the reactions increases the rate, so if there's more. And then there's this idea of a catalyst. A catalyst is something that facilitates the reaction. And in biology, enzymes are the catalysts. And we will talk more about that at a future date. But a catalyst is something that kind of sparks the reaction to happen. Without the catalyst, it doesn't happen very easily. With the catalyst, it happens more easily. And the catalyst is left unchanged by the reaction. It's just involved as an intermediary. So if you're forming the bonds, the person that introduces you to your spouse is the catalyst. There's a chance you'd meet, but that mutual friend becomes the catalyst of forming the bond. But that friend doesn't enter into the relationship. It's left unchanged by the relationship. So we will continue with chemistry part B in another video.